Assalamualaikum everyone. Bertemu lagi kita di session yang kedua. So today I will continue with the chi-square distribution, which is you are familiar with this PDF of chi-square, where the parameter for chi-square is new. Okay, the parameter for chi-square is new. This notation for chi-square: if x is a chi-square with a new parameter. This is the PDF of the chi-square that you have memorized before this, and you also know that the mean for chi-square is new, which is its parameter, and the variance for chi-square is 2 multiply its parameter to new, and you also have memorize the MGF for chi-square distribution. Okay, so let's see the example of 2.5. I believe that all of you can answer these questions. If x has a chi-square distribution with 3 degrees of freedom, find the mean and the variance and write down the MGF for x. So we know that we can write as x is a chi-square distribution with 3 degrees of freedom. So its new will be 3. Find the mean. So the mean, the notation for mean is expected of x. The mean for variance is its degree of freedom, which is 3. And the variance for the chi-square is 2 multiply its parameter, which is 2 multiplied by 3. So the variance is 6. In 2 seconds, you can write down all the mean and the variance of chi-square if you can memorize all of this. Okay, and then you can write down the MGF for chi-square distribution, which is 1 minus 2t power of negative new, which is 3 divided by 2. So this is the illustration of the chi-square distribution with 3 degrees of freedom. Alright, I move to the theorem 2.5, saying that if x has a standard normal distribution, then x square will be chi-square distribution with 1 degree of freedom. If x is standard normal distribution, and x square will be chi-square 1 degree of freedom. Actually, you have proved this in the previous chapter when I give you tutorial before this. You have proved that when x is standard normal, then x square will be a chi-square with 1 degree of freedom. Before this, you proved that using the transformation technique. You can recall back and see the solution that you do before this in chapter 1 in the tutorial. Okay, so this theorem you need to memorize. Okay, another theorem that you need to memorize, which is this theorem, which is when x is standard normal, then x square will be chi-square 1 degree of freedom. Remember that. Okay, so let's say this one. Example 2.6a. Okay, 6a first. V1 and V2 is a standard normal distribution. So what is the distribution for y, which is V1 square? We know that V1 is standard normal distribution. So V1 square will be chi-square 1 degree of freedom according to this theorem. If you can memorize the theorem, no need for you to do the solution, all of that using the transformation technique. Okay, so you can just write down the distribution for V1 square will be chi-square 1. Alright. Okay, the next theorem is for chi-square distribution. We look at theorem 2.6. If x1, x2 until xn are independent random variable having standard normal distribution. So I can write it as xi, because x1, x2 until up to xn. So x1, x2, xn until xn, all of that is a standard normal distribution. Okay, so we can say that according to the previous theorem, if x is standard normal, so x square will be chi-square 1 degree of freedom. So if y is x1 square plus x2 square until up to xn square, it will be summation of xi square. We'll have the distribution of chi-square with n degree of freedom. With n degree of freedom. So how we can prove this? We should start with to find the MGF for y. Okay, to prove this, I will use MGF technique, which is moment generating function technique that you have learned before this in chapter 1, the third technique, remember? Okay, so we will start with to find the MYT. So it will be expected of E T Y. So y is summation of xi square, right here. So we can write it as expected of t x1 square plus t x2 square up to t xn square. Alright, so I can write it as mx1 square t multiply mx2 square t. Is it true? And until mxn square t. Okay, so why I put here mx square? Before this, here should be mx1, mx2, myt, right? mzt, mut, only u, not square. Okay, why I put here mx1 square? Because I know that x1 or xi square is a chi-square 1, and I know and we already know the MGF for chi-square. Alright, so we can write down here the MGF for chi-square. So it will be m1 square. Okay, sorry, mx1 square t is the MGF for chi-square 1. mx2 square t also the MGF for chi-square 1 until mxn square t also the MGF for chi-square 1 according to the previous theorem. So the MGF for chi-square will be 1 minus 2t power of 1 degree of freedom, so it will be negative 1 over 2. This is the MGF for x1 square. The MGF for x2 square is also 1 minus 2t negative 1 over 2 until MGF for xn square will be 1 minus 2t power of negative 1 over 2, because all of these x square having the 1 degree of freedom of chi-square. So what happened when you multiply the same thing? It will be, you can add the index, right, of the variable. So it will be negative n over 2. 1 plus 1 plus 1 plus 1 plus 1, it will be n. So it will be negative n over 2. So this is our final MGF that we get, the MGF for y. This is our y just now. Okay, so this MGF, observe this MGF. This MGF looks like the MGF for chi-square, because of it will be 1 minus 2t, but maybe with a different parameter. So what is the distribution for y? It will be chi-square with parameter n. We proved that y, which is the summation of xi square, is chi-square with n degree of freedom. That's how you prove this theorem. So basically, when you want to find the distribution for the special distribution, like I said before this, I suggest you to use the third method, which is MGF technique. Okay, MGF technique that you have learned before this in chapter 1. Because of now we deal with the chi-square distribution, we know that chi-square distribution is one of the special distribution. So because of that, to prove to know the distribution of any random variable that deal with the special distribution, we use the third method, which is MGF technique. Okay, we move to the next theorem, which is theorem 2.6.1. If x1 until xn are independent random variables having chi-square distribution with nu1, nu2 up to nu(n) degree of freedom, which is, we can write it as x1 having chi-square nu1 degree of freedom, x2 having chi-square nu2 degree of freedom, up to xn having also chi-square with nu(n) degree of freedom, which is all the degree of freedom for this random variable x1 until xn is different. Okay, x1 having nu1 degree of freedom, x2 having nu2, xn having nu(n) degree of freedom. So now we want to prove that the theorem saying that if y is the summation of xi, we'll have the chi-square distribution with parameter nu1 plus nu2 until nu(n) degree of freedom. x1, x2, xn also the chi-square distribution with the different parameter nu. And y, which is the summation of xi, will be also chi-square distribution with nu1, nu2 up to nu(n) degree of freedom, which is you just add up all the degree of freedom for x. How we can prove this? Using the same method as previous. Okay, we start with using the MGF technique. So we start with MYT, so it will be expected of ETY. Y is summation of SI, sorry, should be T here. Okay, so it will be expected of ETX1 multiply ETX2, is it true? ETXN. We also can write it as mx1t, mx2t up to mx and t. We know that x1, x2 until xn is chi-square distribution with the different degree of freedom. So mx1, so x1 mx1t will be the MGF for chi-square with parameter nu1. So it will be negative nu1 divided by 2. Here 1 minus 2t negative nu2 is the degree of freedom of the chi-square divided by 2 multiply until the MGF for xn will be 1 minus 2t power of negative nu(n) divided by 2. Okay, look at this. You will multiply this. Okay, when you multiply this thing, the index will be added, right? So it will be negative nu 1 over 2 plus negative nu 2 over 2 plus negative nu 3 over 2 until negative nu n over 2. So what happened? The index will be added, so we can write it as like this, nu 1 plus nu 2 up to nu n. Is it true? Divide by 2. Is it true? You will get this when you add this thing, the index, right? So this is our final MGF that we get. So observe this MGF looks like the MGF for also chi-square, but with different parameter. Here is the parameter of chi-square, right? So we can say that y is also chi-square with parameter nu 1 plus nu 2 up to nu n degree of freedom. So it's stated in this theorem 2.6.1. Okay, the next theorem is theorem 2.6.2. If x1 and x2 are independent random variables, x1 has a chi-square distribution with nu 1 degree of freedom, and x1 plus x2 has a chi-square distribution with nu degree of freedom, and then x2 will have also chi-square distribution with nu minus nu 1 degree of freedom. Okay, we can write it as x1 having chi-square with nu 1 degree of freedom. x1 plus x2 will have the chi-square with nu degree of freedom. So according to the theorem, if we know the distribution of x1 and x1 plus x2, we can automatically saying that x2 will have the distribution of also of chi-square with nu minus nu 1 degree of freedom. Nu minus nu 1 degree of freedom according to the theorem. Now look at this example, example 2.7. If y is x1 plus x2 having a chi-square random variable with 10 degree of freedom, x1 plus x2 having chi-square with 10 degree of freedom, and x1 is a chi-square distribution with 2 degree of freedom. Determine the degree of freedom of the chi-square random variable x2. So from here, we can say that according to this theorem, we can say that x2 will having the chi-square distribution with 10, which is here, nu minus 2 minus nu 1 degree of freedom. So we can say that x2 having the chi-square distribution with 8 degree of freedom. Okay, you can answer this question if you can memorize this theorem, but if not, you also can use the technique of MGF to find the degree of freedom for x2. Okay, let's do this. Okay, we start with MGF, right? We know the MGF for y, myt. We know the myt is expected of ETY, which is x1 plus x2. So we can write it as ETx1 multiply ETx2. So it will be mx1t multiply mx2t. Okay, so we know that y is a chi-square distribution. Y is a chi-square distribution with 10 degrees of freedom, so we can write down the MGF for chi-square with 10 degrees of freedom. Is it true? And next one is given that chi-square distribution with 2 degrees of freedom, so it will be 1 minus 2t negative 2 over 2. Is it true? And mx2 is also the chi-square, but we do not know the degree of freedom of it. Okay, so you can see this part, we can multiply this, so the index will be added. Is it true? So you can compare this. So from here you can say that 10 equal to 2 plus nu. So we know that nu equal to 8. Okay, same like this. Okay, so another theorem is theorem 2.7. This theorem is quite important for you to memorize, so you need to hafal this theorem. Okay, it's saying that if x bar and x square are the mean and the variance of random sample size n from a normal population, x bar and x square from normal population, with mean mu and standard deviation sigma. Okay, then x bar and x square are independent, and also the random variable, so the other random variable of n minus 1, which is the sample size minus 1, multiplied by sample variance x square, divided by sigma square, which is the population variance, will have a chi-square distribution with n minus 1 degree of freedom. Okay, so this term is another random variable that you need to memorize. This is a random variable that having a chi-square distribution with n minus 1 degree of freedom. Okay, how can this random variable occur? Okay, we can do the proving. Okay, we can prove this. Okay, so you should start with summation of xi minus mu square. So summation of xi minus mu square will be summation of xi minus x bar plus x bar minus mu. Okay, plus minus x bar plus x bar, so you will get xi minus mu. Okay, so this part will be this part, summation, then square, right? Okay, and then alright, and then because of this is square, so you can expand. Xi minus x bar plus x bar minus mu square. Expand that, so you will get this summation of xi x bar square, this part square, minus 2 x bar minus mu multiply summation, this part summation xi minus bar. Okay, you will get this plus summation of x bar minus mu square. Okay, because of this is the mean, okay, this part it can be n summation, right? Summation of the constant, you will get constant here. Summation of constant will be n of constant itself. Alright, so now this part will be 0. This part will be 0. How? Look at this. Okay, you expand this, summation of xi minus n x bar, summation of xi minus summation of x bar. Summation of x bar will be n x bar. Because of x bar is a constant, you will get the value. So you total up the x bar, you will get n x bar. Here, you cannot put n here because xi here adalah random variable. Okay. So when we expand this, you will get summation of xi minus n summation of xi divided by n. Right? N summation of xi divided by n. So these two eliminate. So we'll get summation of xi minus summation of xi will be 0. Alright? So this part will be 0. When this part will be 0, so all of this will be out. Will be cancelled out. Right? So now we have summation of xi minus x bar square plus n x bar minus mu square. Here, this part. Okay, this part. Right, from this. From this, when you expand, you will get this. Okay, so, and then you should divide each term with sigma square. All these terms divide with sigma square. Okay, divide with sigma square. This term divide with sigma square. All of this divide with sigma square. When we divide with sigma square, okay, look at this. Here will be here. Is it true? Xi minus mu divide by sigma altogether square. Summation. Alright? And then this part, summation of xi minus x bar square is n minus 1 x square. Okay. Try to look at this part. Are you familiar with that? Is this from the formula of s square, which is summation s square equal to summation of xi minus x bar square divide n minus 1. This part is this. Because of that, here we replace with s square multiply n minus 1 will be this part. Alright? Okay. Okay. How about this one? It will be x bar altogether, all of this divided by sigma square. So x bar minus mu over square root of n. Sigma over square root of n. Here, bawa ke bawah. So it will be sigma over square root of n. Altogether we square. So here will be eliminated. Right. So here will be square root of n. Okay. Can you understand? Okay. Alright. So this part, this row, I hope this row will be clear. Right. So I will move to the next row. Okay. Alright. This part, xi minus mu over sigma. X having mean mu variance sigma square. So sigma is the standard deviation for x. X minus its mu divide its standard deviation is the standard normal. You remember? This part is from the central limit theorem from the previous lesson, from first session www. Okay, x minus its mean divide its standard deviation will be z. This part will be z, so z square. Summation of z square. Okay, right, this part remain. And then x bar minus mu divide sigma over square root of n is also z. Remember, x bar, the distribution of the mean. X bar having mean mu and the variance is sigma square divided by n. Remember? So this part is the standard deviation for x bar. x bar minus its mu divide its standard deviation. So we can use central limit theorem. This part will be z standard normal. Okay, z square. Right. Summation of z square. Z is standard normal. Summation of standard normal square. From the previous theorem in this session, which is from chi-square theorem, it's saying that when x is a standard normal, x square will be chi-square 1. Summation of chi-square 1 will be chi-square n. Alright, this part remain, and this part standard normal square will be chi-square 1 from the previous theorem. This part yang kita nak prove tadi, the random variable tadi, n minus 1 s square over sigma square. This part yang kita nak cari, so we denote it as y. So y equal to chi-square n minus chi-square 1. Chi-square can be minus with the chi-square, so it will be chi-square n minus 1. This is the proving how we get the theorem of 2.7 just now. Okay, let's do this example. Example 2.9. The claims that the variance of a normal population is 25 is to be rejected if its sample variance is s square, of a random sample of size 16 exceed 54.668 or less than 12.102. What is the probability that the claim will be rejected? So stated here, the claim will be rejected if the sample variance s square exceed 54.668 and less than 12.102. So we can write as, to find the probability of the sample variance exceed 54.668 plus, because of or, so we need to plus probability of the sample variance less than 12.102. Okay, so to find the probability, we need to know the distribution here, right? We need to know the distribution here. So, according to the theorem, we know that the random variable x square n minus 1 over sigma square is a chi-square distribution. So we can have the distribution here, so we can find the probability. Okay, so because of here, we multiply with n minus 1 and divide by sigma square to make this part is a chi-square distribution. So this part also we need to multiply with n minus 1, which is 16 minus 1, divide sigma square, which is 25. Okay, same here, you need to do the same thing. Less than 12.102 multiply 15 divide 25. So we know that this part is a chi-square with n minus 1 degree of freedom, plus also here chi-square n minus 1 less than just the value. So you should find this part, and then to find the probability, please use the chi-square table. Make sure you know how to find the probability using chi-square table.